In this video, I'll show you how to implement a custom USB HID device class specifically for joysticks and gamepads using completely custom hardware based on an STM32 microcontroller, a couple of thumbsticks, switches, and a USB 2.0 full-speed connection. As you can see here, this Queen Bee radio control PCB is connected via USB to my host computer, and I'm testing it with a couple online apps to see if the joystick via USB HID is working, and as you can see, it clearly is, and I'd like to show you how to get to that in this video. The hardware design files are freely available on my GitHub repository. If you go to github.com/pms67/queenbee, you can find the native Altium designer schematic and PCB design documents, as well as the manufacturing documents for JLCPCB. If you don't have Altium Designer, or if you just want to browse the design on the web, you can also go to pms67.github.io, where I list some of the designs featured on this channel, and you can use the Altium A365 viewer to view those directly in your browser. For example, the Queen Bee, which we're looking at in this video. In your own time, you can check through the schematic, as well as the PCB design, and then check out the 3D CAD as well. A huge thank you to JLCPCB for sponsoring this video. I had these Queen Bee radio control PCBs manufactured and assembled by them in China, and they did a fantastic job. As we've just seen, if you go to my GitHub profile, links in the description box below, you can order your own set of Queen Bee radio control PCBs directly from JLC. I've made the design files and manufacturing files compatible for them. Also, at the time of making this video, they do have a Black Friday offer where you can get up to $252 off by following the link in the description box below. At the moment, JLC has some pretty incredible pricing on 6, 8-layer and more PCBs. For example, 8-layer PCBs 50 by 50 millimeters with VNPad ENIG surface finish for only $2 plus shipping, which is pretty incredible. So I'd strongly suggest you check that out, as well as their in-house production and assembly as well. Again, links in the description box below. A big thank you also to Altium for sponsoring this video. I designed these Queen Bee radio control PCBs using Altium Designer and the powerful features that Altium 365 brings to the table, such as library management, supply chain and BOM management, and much, much more. I use Altium A365 for my private and work life as well, and I'd strongly suggest you check it out. Make sure to go to altium365.com/YT/Phil's Lab, and you can get yourself an Altium 365 free trial. In this video, we'll be going through a very small subsection of the USB Human Interface Device class, or USB HID class for short. The USB HID is a standardized device class that enables very easy interface between a custom device to, for example, a host computer, or from a host to a device. You're probably using USB HID capable devices at the moment. They include keyboards, mice, and game controllers, all over a standardized USB interface that we don't have to change particularly much of the protocol ourselves. All we have to do is pass some information to these standardized human interface device classes, such as how many buttons we have, what joysticks we have, their ranges, and that then communicates with the host to enable communication to and from. In this particular video, we will only be looking at a small subset, and that's how to implement a gamepad or joystick type HID class. For this, we have this Queen Bee PCB we saw at the start of this video, which features a couple different interface devices, such as encoders with push buttons. We have thumbsticks left and right, as well as some small toggle switches along the perimeter of the board. To keep it simple, all we're going to be doing is interfacing the STM32H7 microcontroller in the center of this board with the left thumbstick, which is an XY thumbstick, but it also includes a switch or a button. And we have the same thing mirrored on the right-hand side. Again, XY axes, which are basically just potentiometers plus an additional button. And we have these slide switches left and right side. So in total, we have 4 buttons or switches and 2 sets of joysticks or thumbsticks, both with their own XY coordinates. So rather than a mouse just having XY coordinates and a couple of buttons, this is a tiny bit different, and we'll implement it as such as a joystick or as a gamepad, and then we'll do a test later on to see if Windows My PC recognizes this and we can interface with certain applets online. The reason you might want to create a USB HID class for custom hardware is that you could, in this case, use this device, this controller, either as a dedicated game controller if you want, although this is not particularly ergonomic, or you could use this as some sort of hardware in the loop test where you control a flight simulator. For instance, quite some time ago, while I was at university, I wrote my own flight simulator, and you could quite easily integrate your USB HID class to control the aircraft in this particular Unity flight simulator. That would just be one example. But of course, you could create your own keyboards, your own mice, and this is very, very useful to know the basics of USB HID. We will only be scratching the surface and not going into particularly much depth on HID. I just like to show you how you can get going so you can very quickly get up and running on your own. But I will leave a couple of different resources on HID, which is a rather involved class, in the links in the description box below. For example, application note AN249 by Silicon Labs, which goes into quite a bit of depth of how HID works and typical workflows. But we'll all see some of this in this video. We start off as usual with STM32 CubeIDE. We'll start all the way from the beginning, creating a new project. So top left, file, new STM32 project. I'm choosing, in this case, the STM328743IIT6 microcontroller project name, and I'll be writing this in C, and then we can click finish. For now, we will not apply a default configuration for this Cortex M7 core. We'll just run everything without optimization for now. Now we have to set up the peripherals, interfaces, and pin out. For this, of course, we need to follow the hardware that we have. For this, I'll go to my GitHub page, the Altium A365 viewer. In this particular hardware design, what we need for this video are to know that we have a 26 MHz CMOS oscillator input to the high-speed external input. We have thumbsticks left and right, which are essentially potentiometers, which map to relevant ADC channels of the STM32H7. And we have 4 switches. We have a switch per thumbstick, and we have the slide switches on the top left and top right, which should just map to any old GPIO input. We're not going to be using interrupts for these. We're just going to poll them because this implementation is rather slow. If we jump over to the schematic, we can look at the thumbsticks. You can see here they are basically just potentiometers. I'm adding a small filtering capacitor at each output and feeding that directly to the ADCs. For the switches, I'm just passing them through a low-pass filter to GPIO inputs. And then looking at the microcontroller side, we can spot where the CMOS oscillator input is, where, for example, the thumb switch inputs are, as well as in this case, we have the second thumbstick maps to ADCs at PC4 and PC5. So that's what I'm going to move over to CubeIDE. So I've moved over the ADC and GPIO inputs just by simply finding the pins, clicking on the relevant pin I want and selecting what peripheral I want. So in this case, the ADC for this pin, and for the right thumbstick switch, I just set that as GPIO input, and then I can right click on the pin and enter user label to give it somewhat of a sensible name. Before we configure the ADCs and GPIOs, I also need to add the CMOS oscillator input. So I'll go to the top left system core, go to RCC, high speed external clock, and change that to bypass clock source, which then enables this single bottom pin P80, which is my CMOS oscillator single input pin. Remember, this is not a crystal, this is actually a dedicated CMOS oscillator. Also in this RCC section, the bottom we can see system parameters. I'm actually running this system off 3 volts because later on this will be running from a battery and I want to drop my main system voltage a tiny bit, so that's at 3 volts. What we also have to enable on the bottom left, if we go to trace and debug, is of course our debug interface. I happen to be using serial wire debug, so I'll just enable serial wire. We're almost there, and we can almost actually configure the peripherals, but we do also need USB. So I'll go to connectivity on the left-hand side, and I'm using USB full speed with integrated physical layer and change that to device only. This will be a device connected to my host PC, and that enables the differential pair for USB at the top P11, PA12. Before we start setting the peripherals, what I'd like to do is adjust the clock configuration. I will select no for now. We don't want to run automatic clock issue solver. On the left-hand side, my input frequency taken from the schematic is 26 MHz from the crystal oscillator, and I want to use the HSE, a high-speed external CMOS oscillator, as my PLL source mux. So I can either manually configure all of this to give me the right values, for example, for the ADC, core frequency, USB frequency, and of course the core as well, or I can just click resolve clock issues. The way then I've configured my clocking is adjusted the PLL values to give me a 480 MHz core clock and to give me 100 MHz core clock for the ADC and 48 MHz core clock for the USB. We'll also need to know the timer clocks later on, which happen to run at 240 MHz across all of the buses. With this in mind, let's go back to the pinout and configuration. As we're still on USB on the go full speed, I will enable all the interrupts. Now let's move over to the ADC configuration. The ADC channels I've configured, or at least partially configured, are for the thumbstick potentiometer readings. So that's the left thumbstick X, which is channel 4, left thumbstick Y, channel 8, right thumbstick channel 9, which is X, and right thumbstick Y, which is channel 5. These are all single-ended conversions, so that's what we have to enable. So channel 4, I'm going to enable as single-ended. Channel 8 is already enabled single-ended, and channel 9 is already enabled single-ended, and channel 5 also needs to be single-ended, so I'll change that right here. This particular ADC of this particular STM32H7 can go up to 16 bits resolution, which we could actually use for our HID class, but just to keep it simple, I'll go down to 8 bits of resolution. I don't need particularly high resolution in this case. So I'll select 8-bit resolution. We'll also configure this with DMA and a timer, and I do have previous videos on this. If you'd like to go into more detail, I'm just going to fly over this a tiny bit because you want to get to the main HID part. What I'm going to change is the number of conversions because you want to sample 4 channels at every sample time. So I'm going to change that from 1 to 4 because we have 4 input channels, the thumbstick left and right, X and Y. The external trigger conversion source, rather than being launched by software, I'm going to select timer 3 trigger out event because I'm going to be using timer 3 rather arbitrarily as my sampling timer. So I might sample these at 100 Hz. That means I could do some low pass filtering before we pass them to the HID, or we can run them at 10 Hz, whatever frequency is suitable in your case. But for this case, I'll use a timer 3 trigger out event. The end of conversion selection, I'll change to end of sequence of conversion, and then we can adjust the ranks. So I'd like to sample thumbstick left X, Y, right X, Y. So we need to do 4, 8, 9, and 5. So I'll change my ranks to be 4, 8, 9, and 5. So this is just saying the sequence of conversion, how the channels are going to be stored one after each other. The sampling time is the number of cycles based on the core clock of the ADC. If we go back to the clock configuration, the core clock is 100 MHz, so it's very, very fast. We don't need to sample that fast. So therefore my sampling time, I'm just going to tone down to something like the slowest 811 cycles for all of these channels. We're almost done, but I'd like to enable the ADC interrupt as well as DMA, because we just want to sample and store all of these samples in the background. So I'm going to add DMA request for ADC1. Direction is peripheral to memory from the ADC into memory, and we'll give this a slightly higher priority if we happen to have other DMA streams running. The mode is circular because you don't want to have to keep restarting the DMA streams, and the data width is byte because we're using 8 bits of ADC channels, and that's all we need to do here. Go back to parameter settings, and the conversion data management mode is DMA circular mode. So now that we've set this up, remember we also need to set up the timer 3, which is our conversion timer. So I'll go to timers, timer 3, clock source internal clock. We don't have to enable any channels, we just want this timer to run in the background. And we have to set the prescaler and counter period to give us a suitable conversion time. Going back to the clock configuration, we can see that all of the timer clocks in this particular case happen to be 240 MHz, so we don't have to figure out if it's the APB1 timer clock or APB2. If you have different timer clocks, you have to go to the datasheet and figure out which APB bus your timer is attached to. The way to get the base or sampling frequency of our timer is take our core timer frequency, which in my case was 240 MHz, so 240 times 10 to the 6, divide that by the prescaler and divide it by the counter period, and that gives us our base frequency. I like to have my counter period go up to 100, so in terms of percent, even though in this case it doesn't really matter. So my prescaler will be 24,000 to give me a sampling frequency of 100 Hz. This is what I'm going to take over to timer 3, so the prescaler was 24,000, but it turns out that internally 1 is added to this value, so I'm going to subtract 1 to give myself an accurate prescaler value, and the same thing for the counter period, so 100, but 1 gets added later on, so I'll do 100 minus 1. Lastly, the trigger event selection needs to be set to update event to make sure every time this counter overruns, we trigger the ADC to sample. So it's slightly a bit involved, and of course it depends on your use case, but I just wanted to show how I would set that up to just run in the background. Now we've set up the ADCs with the conversion timer and DMA, we also have these GPIO inputs. I happen to have pull-ups and filtering externally, so I don't have to set anything up for the GPIOs themselves, and we're not running interrupts on these GPIOs anyway. The final thing we have to do before we can actually get to the HID part is actually enable ST's own HID class implementation, which is very, very useful and takes away most of the work from us. To do that, we go to the left-hand side at the bottom, go to Middleware and Software Packs, and navigate to USB device. We're using a full-speed implementation, and I'll change that to Human Interface Device Class, HID. Now, the reason I'm using Human Interface Device Class, not Custom, is because for the sake of time in this video. The better thing to do would be to use Custom Human Interface Device Class, because if you make changes to the IOC file using Human Interface Device Class, every time you regenerate code, it'll overwrite what you've already done. So I'd strongly suggest selecting Custom Human Interface Device Class, but I'll leave that as an exercise to the viewer. Just for the sake of time, I'm going to go with Human Interface Device Class and edit some of the already available parameters. What will be important also later on, or generally for your device, is this interval. And this, for a full speed implementation, not USB high speed, so full speed, is the number of milliseconds the host waits before repolling from the USB device. So in the case of hex A, which is 10 in decimal, every 10 milliseconds the host will request data from the HID device. And this is pretty good for example, a joystick or a gamepad where you want a fairly quick refresh rate. So 10 milliseconds might be completely fine. You might want to go something slower, depends on what device you're using. This is one of the main parameters to pay attention to. The rest for now we don't really need to take care of. If we go to the device descriptors, we can change the vendor ID, the product ID, product strings, and so on. Now keep in mind, this depends on if you have your own vendor ID, which can be very costly, or if you're subletting, so to speak, one from your processor manufacturer, or if you've gotten a free PID, for example. Now, this is something you should really only do if you do have a real PID VID, but I'm going to change the manufacturer string and product string to something a bit more cool than what is already here. Now, with all of this in place, I can hit Ctrl+S, which will auto-generate some code for me. With our main framework now generated, at least that in code, we need to start by adding in our ADC acquisition. The way I will do that just in this very simple case, I'll create a define of the number of ADC channels we're using. This happens to be 4. And I will create a buffer to store our unsigned integers of ADC data and initialize them all to be 0. So the DMA will then in the background, through timer 3, which currently samples at 100 times a second, will fill this ADC buffer with our thumbstick potentiometer readings. Then in int main, after all the peripherals have been initialized, we'd like to start the ADC as well as the DMA stream as well as the timer. Before starting the ADC, what I typically like to do is do a calibration using the HAL ADCX calibration to start. We can find a bit of documentation on this if we go on the left-hand side of the project structure, go to drivers, HAL driver, source, and go to ADC_EX. These calibration functions are in this ex.c.h files. And we can see we have calibration start, which takes in the ADC handle, takes in the calibration mode, and if it's single or differential. We'll just go with calibration offset, and we're using ADCs in their single-ended mode for this particular example. So that's exactly what I've done here. After the calibration is complete, I'm going to start the ADC stream with DMA, and after that we'll start the timer, and for this we simply pass the ADC1 handle, and we pass our buffer, which we defined before as this volatile uint8 type ADC buffer. With 4 channels, we have to cast it to a 32T type, and then we also have to pass how many channels we actually want to sample. This is all part of the hardware abstraction layer, so this is very, very simple. Finally, to actually start the conversions, we need to start our timer, which in this case was timer 3, so we'll just use the Altium base start function. If we go to the HAL ADC driver, we can see on the right-hand side there's a conversion complete function which is weak, which we can define ourselves if we want to do something when the conversions have been completed. I'll copy that definition over so we can set a breakpoint and see if we are actually getting readings out. With this very basic structure in place, let's just check that the ADC readings are being handled correctly. So I've connected my board via USB and serial wire debug via tag connect header and an ST link. I can then click on the debug icon at the top, which will build this project, hopefully with 0 errors, 0 warnings. And then we can just use the default debug configurations and click OK. Then the first breakpoint is set directly in int main. I can click F8 or resume at the top left to start the program and set a breakpoint in the conversion complete callback. And with any luck, we actually do hit this callback, which means it looks like the ADC is actually being triggered, but now we need to see if the data buffer is actually being filled. So I'll remove this breakpoint, click continue. I'll copy the name of our buffer, and on the right-hand side in the live expressions panel, I will type in the expression for ADC buff, and then expand that, and we can see our array of 4 ADC channels. So if I move my thumbstick, this is now moving the left one on the x-axis and the y-axis, and moving the right thumbstick, we can see we're getting 8 bits of data from our ADC buffers for the left and right thumbsticks. So this is already looking pretty good. So I'll stop this program for now. And we can also now add in the polling button reads, and I'll do that in the main while loop. The way I can do that is called HAL GPIO read pin, and I have to specify the port and the pin name. The port and pin name you can find by going to main.h, so control clicking here. If I scroll down, I can see the private defines added by CubeIDE. We can see that we have the thumb switch left GPIO port and pin, so I'll just copy those over to do polling reads in my various switches. Something very simply like this. This is for all of the 4 switches. I'll set a breakpoint at 124. I'll build this project and then I'll click in debug mode, and then we can just read if we're actually getting switches in or out. Once the program has been loaded, click on resume or F8, and I've set the breakpoint already at 124. I can hover over these switches and see if they're set or not. For the thumbsticks, left and right switches, I have pull-ups by default, so once I press them, they will actually go low, so it's inverted logic. And for the switches, because of their orientations, if the left switch is low, it's going to go to 0. If the right switch is pulled down, it actually goes to 1 because of the 180-degree flip in their orientations. So this is something we would have to adjust to get the polarities right, but at least we're getting these values being read out. Therefore, what I'm going to do is I'm just going to invert the logic for the thumb switches and the right switch. So in this case, we have consistent defines for the logic of these switches. Now that we've tested our ADCs and GPIO inputs, we now have to link our ADC readings as well as our GPIO inputs, our switches or buttons, to the HID class. To start off with, let's do a bit of a dive into the USB HID.h.c files, which form the core, or one of the cores of this particular class. Luckily for us, we don't have to change typically very much, but the HID implementation and the way you report back your readings can be very finicky, and you have to get it 100% right, otherwise it will not work. On the left-hand side in the project tree, we can go to Middleware's, ST, the USB device library class, and then the folder HID, which includes the HID.h and the HID.c files. Let's just open HID.h and have a quick browse through. A lot of this you can leave as standard and as default. Of course, it can change if you have different HID needs. If you do composite devices or completely custom implementation, you will have to change this, but for us, we do not have to do this. One thing we can recognize again from the CubeIDE config is this HID FSB interval, which is our polling interval from the host to the device, which is currently set at hex A, which is 10 in decimal, so 10 milliseconds for the full speed implementation. So you could change that here if you want to go faster or slower. If we scroll further down, we do have a function definition, which is USB-D HID send report, and the report is a report or a list of variables or data you send back from your device, in this case our STM32, through the USB interface to your host. And this report contains, in our case, the button switches, the coordinates for X and Y for each of the thumbsticks, and that will then tell through HID, through a standardized interface, what to do on the host end. So you can then map those values to, if you're playing a game, if you have a flight simulator or whatever, you can map those from your joystick or gamepad. So we'll be using this HID send report later on. The question is, how do we fill in this report? Do we just pop in some random variables, our button switches and ADCs? The answer is, unfortunately not. There's quite a specific structure we have to adhere to, and we have to actually change this report structure depending on what system we have. So now let's move over to HID.c. And luckily for us, most of this code has already been written, but it has been written for the class of mouse. One of the important structs in this file is the USB HID config description or descriptor. Most of this you can leave as standard. You might need to change the number of interfaces, again, if you have custom HID needs. This tells the USB host if we are self-powered, what type of device it is, how many interfaces we have, and more. In this particular instance, ST has by default implemented again a mouse class, and we can see that in line 161, this 2 value here, and they've kindly written that at the interface protocol, 0 is none, 1 is keyboard, 2 is mouse. So by default, they're assuming a mouse interface, so if you happen to upload this directly to your board, connect by USB, most likely a mouse will pop up if you send the right report. In our case, we actually don't want a mouse, so we want type none. We want a joystick or a gamepad, which we'll define later on. So you can change this to 0. Above that is also an interface subclass, which is boot or no boot. And this, very simply, is if this device needs to be available at boot time before the operating system is fully loaded. For a case of a mouse, of course, that can be very useful, but for a gamepad or joystick, not so much. So we'll change that from 1 to 0, which indicates no boot. One more thing we'll have to change in our specific implementation is this mouse report descriptor size, which will actually be changing to a joystick or a gamepad report descriptor size. It's just the name that changes, but the actual underlying number is what we need to change, or the size of the report. Again, we will be sending back the button presses or states, as well as the ADC readings. And here we can see we're also passing in the HID FSB interval, which again was the polling time in milliseconds for full speed implementation. Then we have an HID descriptor, which for now we're not particularly interested in, but again, notice here we're passing over the report descriptor size. Then we have a device qualifier, and now most importantly for us, what we have to change is the HID mouse report descriptor. This report descriptor has a very specific structure and very specific subsections. To me, this kind of reminds you a bit of XML, where you have these various subclasses and various parameters or objects within. If we just look at the mouse report, we can see we have a definition for a button, and here we're saying we actually have 1, 2, 3 buttons with 2 logic states, either a 0 or 1. So here we are defining 3 buttons for our mouse. Then after that, they are defining an X and Y coordinate as well as a wheel coordinate with minimums of -127 up to 127. So they're mapping the X and Y as well as the mouse Y wheel to -127 to +127 using these standardized HID parameters in the specific report. Overall, there's quite a lot of detail to these HID report descriptors, and it can sometimes get quite overwhelming, especially one small change might break the whole system and your device might not even show up at all. I'd strongly suggest reading through at least the basics of HID report descriptors. I'll leave some links in the description box below. Adafruit also has one of these beginner guides to writing USB HID report descriptors, which also links to the Microsoft HID Tools project, which will help you create your own HID report descriptors. What I'd also strongly suggest is just finding open source implementations for your particular device and then modifying them. For example, in this video, I'll show you how I did it for my particular setup with 4 buttons and 2 thumbsticks, and you can use that as a template if you have more buttons, less buttons, more thumbsticks or not. I also downloaded this HID Descriptor tool, which shows the main HID items. If I double click on one of these, this will show me available parameters for these particular HID report descriptor parameters. Now, I wouldn't use this tool on its own. Again, I would reference an openly available descriptor and adjust that, but this tool can be very useful for finding out how does a logical minimum, let's say of 8, map to the actual bytes you have to send over in the descriptor. So this is a tool I've used while I was implementing this myself. The actual report descriptor I then came up with was pieced together from some open source documentation, as well as adjusting for my particular needs. I'd strongly suggest following this and then adjusting based on your needs, but let me just go through briefly. The first section is the usage page, and for the type of joystick, this falls under generic desktop controls. Then the subclass of the usage is actually a joystick, but you can also select a gamepad. Joystick happens to be number 4, mouse number 3, keyboard number 2, gamepad number 5, and so on. Again, use the HID tool or an online search to find out what device you want to use. Then there are these subsections, which are collections, which define what the joystick is used for. In this case, it's a pointer. And then what the physical attributes are of that particular device, in my case a joystick or a gamepad. And this section is the most important because this defines what the host will get in terms of information, and then also lets us know how we need to package that information via the send report function. The first bit you always have to add is a usage page, and the usage page, if I double click in the HID tool, can be any of these values. So it could be LEDs, buttons, controls, whatever. In my case, I want to add 4 buttons. So I did usage page hex 05, hex 09 using the HID tools, and then you define how many buttons you have. I happen to go from index 1 to index 4, so I have 4 buttons. Then you have to define what the values of these buttons can be. For a button, there's either on or off, so my logical minimum is 0 and my logical maximum is 1. Then you define how many buttons you actually report or you send in this particular report, and this is the number of buttons, so it's simply 4. And there is one report of 4 buttons. This whole thing is slightly confusing. I did have to piece this together quite a bit myself, but this is what I came up with. The actual report count 4 is not bytes, it's bits. Because we are using a single bit to define the button state, we only have 4 bits, but HID reports require them to be divisible by 8, so therefore we have to pad these 4 bits with an additional 4 bits. Therefore I'm creating an additional report of size 4 bits for simple padding to give me 8 bits in total for this particular usage page. Then we create a new usage page. We've defined our 4 buttons now because we want to have 4 axes of joysticks. And this needs to follow a particular order again. We can't simply have 2 X's and 2 Y's. There are some predefined HID report descriptor values for joysticks. So I define my X, my Y, which is for my left thumbstick, and my right thumbstick happens to be mapped to, or needed to be mapped to, the following values, which is Z and the rotation about the X-axis. These are just standard joystick definitions. Then, because they are not buttons, they are joysticks, we need to have a different range, not 0 to 1. We might want to do 0 to 255 or 0 to 65535, depending on how many bits we have. We have 8 bits, and the preferred mapping, at least from what I can tell, is from -127 to +127, so symmetrically about 0. So this isn't the full 8-bit range, which would be -128 to +127. This is truncated to -127 to +127. The report size is 8 bits to cover the range per joystick axis value, and we have 4 report counts because we are passing in 4 thumbstick readings of the potentiometers. I'll add this project to the GitHub repo so you don't have to memorize and copy this over yourself. Keep in mind, I did a lot of this by simply piecing together work from open source projects and also using this HID tool to do some trimming. But the important thing is that you do adjust this report descriptor. I've added in the 4 buttons and I've added in the 4 thumbstick readings. After you've adjusted your report descriptor based on your needs, you also need to adjust the report descriptor size definition. If I control click and follow that used to be 74, but I changed it to 54. It's the number of bytes in your descriptor. Again, keep in mind, I'm just keeping the names here, such as mouse, but you of course want to create your own custom HID class and change that to whatever you want, if it's joystick, gamepad, keyboard, or whatever. I'm just keeping this in for the time and simplicity's sake. But now that we have our report descriptor size changed and we actually have a different report descriptor based on our hardware, we now need to send the report. Back in main.c, I've pasted in this struct. I've just called it joystick report, and this depends on what hardware you're using. We are going to then take this struct and send it using the send report function from the USB-D HID class driver. Remember, for us we had 4 buttons, which are actually being sent as 1 byte, so 4 bits plus 4 bits of padding. That's why I have only a single U8T variable here, which will have our 4 bits of button presses. Then we had a -127 to +127 range for all of the joystick axes. So that's the left joystick X and Y and right joystick X and Y. So therefore I've got 4 int8 type, so signed 8-bit integers, left thumbstick X, left thumbstick Y, right thumbstick X, and right thumbstick Y. We will then simply fill in this data, package it, and send it out via the send report command. It is actually that simple. The way we'll package this is that the buttons will just set when we're pulling, and the thumbstick will just do in the ADC data callback. So what I'll do, I'll just create a private global variable of the joystick report and call it container. In the conversion complete callback, I'll set the thumbstick left X value to be ADC data 0. I'll set that to be ADC buff 0. And remember, ADC buff is actually unsigned integer. So we have to shift 0255 to -127 +127. And a very, very crude way of doing that is simply subtracting 128. Of course, we need to make sure that the value doesn't go below -127 and we want to apply deadband. But for the most simple implementation, something like this will do very easily. In this conversion complete callback, of course, you could do filtering as well, low pass filtering. You could do specific nonlinear mappings depending on your specific needs, but something like this just to fill up this report container with our ADC readings for now is just a basic example. Then scrolling down to our while loop, remember we had done this polling read of the 4 switches. What we have to do is combine those individual bits into our single byte button variable. So 4 of the bits will be populated, the rest will be zeros. And of course, now the order is important. The order of these switches is then how that'll show up on our host device. So I've just taken the individual bits and left shifted them by the amount they need to be. So I have 4 bits occupying half of this button's 8-bit variable. What we then have to do is then finally send the report. To do so, you will call the USB-D HID send report function, which is part of USB-D HID.C and .h. This will take the USB full speed device or handle type def in our case. It'll take our struct and we'll cast it to an array of U8T type variables or pointer. And we have 5 elements, 5 U8T size elements in our struct. You can use size of, but that can cause issues depending on alignment of your struct size of. It doesn't always return the exact number of bytes. HUSB device FS, you do have to define as extern somewhere in main C or wherever you use the send report function. Then after send report, because we defined our B interval as 10 milliseconds or hex A, the host will poll every 10 milliseconds. So that's where I'm just very crudely adding in a delay. Of course, you might want to do this on a timer if you don't want anything blocking. But for now, we'll just keep this very, very simple. I'll click build and then I'll click run and upload this code to my board, which is again connected via USB and serial wire debug via an ST-Link. On Windows, you can go to your search bar and enter game controllers. If I click on the game controllers in the control panel, what we can see here is our controller has been identified. Now, if I double click on this and go to the test panel, and now if I move my left thumbstick, we can see the XY axes are actually being mapped seemingly correctly to this test setup. So if I move my right joystick, if I just do it on the Y axis, or the X-axis, at least seen from the joystick's perspective, these are all identified as the axes because we've developed our report descriptor properly. What we can also see are these buttons, 4 buttons on the bottom side. So if I do my thumbstick left, if I press that down, you can see the first button. Thumbstick right is being pressed. Now if I do my left switch, toggle it on, toggle it off, right switch, toggle on, toggle off, which is pretty cool. Now, of course, you can see there's a little bit of offset here, offsets here, so there is some tweaking to do. You can, of course, increase the resolution of your ADC readings, which means you have to change your report descriptor. But very simply, this is how we set up, very quickly, an HID compatible device using completely custom hardware. This then also works with most games or online applications. I just typed in USB controller or Gamepad tester, got to this website, and this just shows a PlayStation controller in this case, and it's detected our Queen Bee controller. This is the product ID string we changed earlier on in the CubeIDE config. And now if I move my left joystick, you can see visual representation on this site is actually showing the left joystick moving. Then the right joystick, I can use my buttons and switches on my thumbsticks, and these happen to be mapped to these particular PlayStation buttons. And let's try the switches as well. These are mapped to the right side pads as well. So pretty cool and very simple. We've set up our USB HID class. Thank you very much for watching this video. I hope it was useful and I hope it showed you the basics of setting up your own USB HID device class on an STM32 microcontroller on completely custom hardware. This will hopefully enable you to control your computer or do specific hardware in the loop testing or control other peripherals via USB. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest embedded systems videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.